box and pointer notation is a way to represent lists within our environment diagrams. So the reason why we need a notation is that sequential data can actually become quite complicated. And that's because of the closure property. A method for combining data values satisfies this closure property if it's the case that the result of combination can itself be combined using the same method. If I can put items within a list, I should be able to take that list and put it into a list. Closure is powerful because it permits us to create hierarchical structures. Hierarchical structures are made up of parts, which themselves are made up of parts, and so on. And that is an extremely useful way to represent all sorts of things in the world. So the important point here is that lists can contain other lists as elements, in addition to anything else. And that means that we need a way to keep track of what's inside of what. That's where we use box and pointer notation. Lists are represented in environment diagrams as a row of index-labeled adjacent boxes, one per element. Each box either contains a primitive value or points to a compound value. So if I just say pair equals the list 1, 2, I'll write that in my environment diagram by binding the name pair to a list that contains 1 and 2. These small numbers in the corner are just indices of the list. And so, since the list has 2 elements, we see 2 adjacent boxes. Now for a more complex example, nested list is bound to a list that contains a list, and another list. And this third list contains lists itself. And within it are all sorts of things, even a function. So let's walk through everything that's on the screen. Nested list is a 3-element list, and so we see it bound to 3 adjacent rectangles. Now each element of nested list is actually another list, and so that's why we see pointers to compound values. Lists are compound values, functions are compound values. Anything that has multiple parts is going to be represented using an arrow to some depiction of that thing. Okay, so here we see that the element at index 0 is just a list containing 1 and 2. The element at index 1 is the empty list. Here we see the empty list. And the element at index 3 is itself a list that contains 2 other lists. And so that's why we see this hierarchical structure, where this is made up of parts which are made up of parts. The primitive values 3, false, and none can be written directly into the box. So can 4. The function we write as we've always written functions before, and we use a small arrow to say that it's contained as this element at index 1 of the list that's within this list that's within this list.